Hello and welcome back. Today we are going to start with another classification, which is rotational versus irrotational flows. Now, if a flow has fluid particles, this fluid particle is not only translating with the flow, but it is also rotating. Suppose if this fluid element taken is, say, square shaped, and these are the labels 1, 2, 3, 4, and since it is going from this position to this position, it is translating with the flow. But at the same time, what happens is each fluid particle is also rotating. So if it was 1 and this was 2, now suppose this is 1, this is 2, this is 3, and this is 4. So not only translation has happened, but also the particle has rotated. Flows in which particles rotate during the flow, such a flow is called a rotational flow. And for rotational flow, the angular velocity of the particle is not zero. So if we take a fluid particle and measure its angular velocity, it will not be zero, it will be something, so because it is rotating. And irrotational regions of flow are those regions of flow in which fluid particle translated but does not rotate at all. So angular velocity of the fluid particle will be zero. Now there will be a single flow field which has two regions. A complete flow field, a flow field is not always completely either rotational or irrotational. Maybe cases, but usually how we study is there is a flow field, it has some regions where rotational effects are significant, and there are some regions where rotational effects are not significant. We can assume those regions as irrotational regions of flow. That's why we always talk about rotational regions of flow, irrotational regions of flow. So this is the basic distinction between if the fluid particles rotate, rotational. If they do not rotate or negligibly rotate, we call it irrotational regions of flow. Now, if we talk about internal flows are viscous dominated, and almost viscous dominated shear stresses exist, and these internal flows are generally rotational, always rotational. The internal flows, we will always see that these internal flows are always rotational. They are viscous dominated. The particle, there will be shear stress which will cause these particles to rotate, and we will always see this angular velocity non-zero. But in case of external flows, we know we have two regions of flow. One is the wake and this boundary layer, which is viscous dominated, and the other is the region away from the body, or in front of the body, or behind the body after this wake region. This is inviscid. And these viscous regions of flows are treated as rotational. They are rotational regions of flow for external flow, and these inviscid regions of flow are treated as irrotational, usually irrotational regions of flow. And this irrotational region of flow, we call this type of flow where there is no rotation of the particle. We study it by assuming it is irrotational. Such a study of flow, such a flow is known as potential flow. So flow which is irrotational, inviscid, we call it potential flow. So rotational versus irrotational flows, we distinguish them by seeing if the fluid particle, if the fluid element we chose, any fluid element we see, if it just translates and does not rotate, it is irrotational flow. If it translates as well as rotates each of the fluid particle, we call it rotational flow. So for rotational flow, angular velocity will be non-zero, and for irrotational flow it will be zero. And other thing that we use is the vorticity, which is curl of the velocity field. We'll see it in later chapters. Angular velocity 0 means vorticity is 0, and angular velocity non-zero means the vorticity is not 0. It's another way of measuring this, deciding whether the flow is rotational or irrotational.